Hello, good morning. So we are moving on to our next section, that is bias compensation circuits. So why do we need a bias compensation circuit? That is the first question we need to answer. Why do we need a bias compensation circuits? So usually for a transistor, in order to stabilize the operating point, what we are doing, we are using different stability, we are using different biasing circuits, okay, in order to stabilize the Q point. What was the Q point? That is VCEQ and ICQ, isn't it? So VCEQ variation is very negligible, but ICQ varies, a collector current varies. So we uses different what circuits? Biasing circuits so that this biasing circuit should be applied so that our operating point should be a fixed point. Okay, so what are the different biasing circuit we have studied? We have studied on the fixed bias circuit, then we have studied on the self bias or emitter bias circuits. Then I have told you about, what is the other circuit I have told you about? I have told you about base collector feedback circuit. Then I have told you about emitter collector feedback circuit, isn't it? Emitter collector feedback circuit, as well as I have given you the most important topic, that is potential divider circuit. Okay, so this is the most important topic and it will be asked for the university question. Okay, if we are referring the previous last year's questions, at least one question will be there. That too will be problem from potential divider circuit. So we have studied all these biasing circuits and we want to measure how much is the collector current varies with respect to the different parameters. What are the different parameters in which the collector current varies? We know that from the equation. I can write it as IC is equal to beta IB plus beta plus 1 into ICBO. I have already told you about collector current, that is IC is equal to beta IB plus beta plus 1 into ICBO. So the factors in which the collector current depends on the term beta, then on IB, and also the minority current carriers ICBO. Okay, so this beta value is unique for a particular transistor, and IB is the input current, which will be always in microwave ampere, but it depends on the input voltage, isn't it? We know that the input VI characteristics of a, isn't it? We know that VI characteristics of a diode, in which it will be like this. After the barrier potential or 0.7 volt, the IB value depends on the VBE. Okay, so when the VBE changes, IB changes drastically. Then we know that minority current carriers are there. What will happen to the minority current carriers? The minority current carriers doubles per 10 degree rise in the temperature. ICBO doubles when there is a 10 degree rise in the temperature. And what will happen when the temperature varies? The VBE, there will be 2.5 millivolt variation happens per degree rise in temperature. Okay, so what are the factors which results in shifting of the operating point or shifting of the collector current are beta value, then temperature. Because of the temperature, the VBE voltage value varies for 2.5 millivolt per degree Celsius, and also the minority current carriers doubles for every 10 degree rise in the temperature. I have already given you a circle diagram, that is, when the current IC flows, there is a heat in the heat, so which will increase the temperature. Then what will happen when the temperature is increased? ICO increases, isn't it? I have given you as if in a circle. Do you remembering all those things we have discussed as far as this temperature rise and all those things? That is a very important question. What are the factors that results in the variation of the collector current? That is a very important question, and you people should be prepared well for writing the same in your answer book also. Okay, so what are the different factors that are affecting this? That is, when the collector current flows, then the temperature increases. When the temperature increases, the kinetic energy of the particle increases. As a result, the minority current carrier also increases. So, for 10-degree rise in temperature, the minority carriers double. So, as a result, what happened? The current, the collector current IC also varies. This is also one important phenomena, that is how the temperature influences the change of the collector current. Okay, so the collector current depends upon what all factors? Beta, IB or VBE and ICBO. And also we know that this is a cumulative process. So as IC increases, temperature increases again, which increases the which increases the minority current carriers. As a result, there will be a cumulative temperature rise and the transistor cannot withstand the temperature. So what will happen? There will be a thermal runaway. What do you mean by a thermal runaway? That also we have discussed. Thermal runaway is the total destruction of the transistor. What is thermal runaway? Thermal runaway is the total destruction of the transistor by the temperature rise. So how can we prevent the thermal runaway? The thermal runaway, you should remember the term thermal runaway. So thermal runaway means the total destruction of the transistor. And how can we prevent it? The preventive measures includes we should reduce the temperature. So either we can give a negative feedback. This happens when in case of this self-biased or emitter bias, we can give a negative feedback. This base collector gives a negative feedback to the base. So here we are giving a negative feedback, or we can also practically give heat sinks. Okay, using aluminum metal, we can give heat sinks. Heat sinks will be a metal, that is, it will be like this. The top view will be like this. Okay. This will, from the top we can see like this, or it will have some fins. Okay, it will have some fins like this. 1, 2, 3. 3 fins will be there in this layer. Okay, so like this, as if we have seen in our glass, it will be like this. Okay, in between space is there, and the aluminum metal will be in this shape. So what will happen? The heat will be easily transferred from the transistor to this fans or fins. Sorry, not fans, fins, so that it will get heated up, and the heat exchange, the thermal diffusion will be from this aluminum metal fin to the air. So like this, we are employing heat sinks on the top of the transistor. Okay, now what we are going to discuss is why do we need this compensation circuits. So even though we are stabilizing the operating point, or we are analyzing the change of collector current with reference to these 3 parameters in order to measure the stability. That is, in the stability factor, we are differentiating the collector current with reference to the 3 parameters to measure the stability of our circuit. So from the stability factor, we know whether our Q point can be stable. How can we know? If the stability factor value is very low, then we can say our circuit is stable. Okay. Now, even though we are giving this negative feedback and we are applying this heat sinks, we are giving all those things like biasing methods, but still there is the chance for the transistor to shift its operating point. Okay, and another major drawback. Okay, there is a first, what is the need of the bias compensation circuit is to stabilize the operating point, and in the second point, what should I tell you, even though we have all this negative feedback and all those things, there is a chance of varying the operating point. And there is another disadvantage that we can say we can prevent the thermal rise or temperature rise by giving a negative feedback. So we are saying we give negative feedback, but what the problem is, the second point is, can you see it? Yes. Okay. So this was the first point, and from the second point we told in order to stabilize we are giving negative feedback. What will happen if we give negative feedback? If I am giving negative feedback, then naturally our amplification factor beta in case of common emitter, or gamma in terms of common collector, and alpha in terms of common base configuration, this amplification decreases. So what will happen when the amplification decreases? It cannot be used for an amplifier circuit. We need proper amplification for a transistor. So then what we are going to do, in order to reduce this negative feedback effect, we will give another circuit. That circuit is known as a compensation circuit. So why do we need compensation circuit? So we need compensation circuits to stabilize the operating point. Okay, or we are giving compensation to the stability of the biasing circuit. Okay, so in compensation circuit, what we are doing is we are giving temperature sensitive devices. In bias compensation circuits, what we are going to do is we are giving thermal sensitive or temperature sensitive devices to reduce the adverse effect. Okay, to reduce the adverse effect, we are giving temperature sensitive devices. That can be a diode, that can be a transistor, or a thermistor, or another is sensistors. Any sensistors can be used to give compensation. Okay, so again we are moving on further. So what we are going to do is we are going to give bias compensation. So what are the different bias compensation circuits? Wait a minute. Okay, what are the different bias compensation circuit? Bias compensation circuits. What are the different bias compensation? We are providing bias compensation by using any thermal sensitive device, isn't it? So usually we provide a diode, or we can provide a thermistor. Thermistor means a thermal resistor, which means the temperature varies, the resistance also varies. Okay, or we can use a sensistors. Okay, these are the three methods of using bias compensation. So we can ignore this, and these two are asked for the university examination. So for the bias compensation circuit we use diode, and this diode bias compensation is used against the variation of VBE and also the minority current ICO. Okay, so diode compensation is used for against the variation in VBE and ICO, and thermistor compensation we know in order to prevent the thermal runaway. Okay, in order to prevent the thermal runaway, what we are doing is we are incorporating a thermistor. Okay, so as the temperature increases, the voltage across the thermistor decreases. So the forward biasing voltage decreases. As a result, collector current decreases, and the increase in collector current due to the temperature will be compensated by improving a thermistor. So thermistor is, as usual, it is used against the thermal variation. Okay. Now, in diode compensation circuit, first we will study on diode compensation circuit. In diode compensation circuit, what we will do is we will employ a diode which will be of the same type of the transistor. Okay, the diode which will be of the same material of the transistor will be used to compensate for the variation of VBE and ICO. Okay, for example, I am simply drawing a simple circuit. Okay, collector, emitter, base of the transistor, and I am giving a simple circuit. Okay, so this is an RB, and here I am giving a voltage VB. Okay, then in the emitter circuit there is we have our resistance RE. So what I will do is I will give a diode which will be in opposite direction as of the junction. Okay, the variation for VBE. First we are discussing on the variation for VBE. So this is VBE. This is positive because this is NPN transistor. Arrow is facing outward. So PN. So PN. In the opposite direction, what I have to give? NP. So I have given cathode and anode here. I have given a diode here. Okay, so I am connecting in the connecting a diode of same material. If this transistor is made of silicon, then the diode should also be made of silicon. So what will I do? I will connect in the phase opposition to this diode is connected in phase opposition to VBE. Okay, then as usual my resistance RC and VCC. Okay, so here we are giving this diode. Okay, so what will I do? So this diode I will be connected through a resistance RD and a separate source. Okay, so this diode, the source is VDD. Okay, so what I will do, I am connecting this diode in phase opposition to the circuit. For what? For compensating against the variation of VBE. How will the VBE vary? Because for every degree rise of temperature, the VBE will be varying by 2.5. So what will happen here is, for if the temperature variation is 2.5 millivolt in this VBE junction, then I have connected this in the opposite direction. So here there will be minus 2.5 millivolt variation in the diode. Okay, and if we are considering in total, this will cancel out. Okay, so the change in VBE due to the rise in temperature is compensated by the change in voltage across the diode VD, so that our output current IC will become insensitive to the variations of VBE. The IC will become insensitive to the variation of the VBE. Okay, so for this, what is our requirement? We need our diode to be of the same material as that of the transistor is made. Okay, so like that we can reduce our we can reduce the variation of VBE. I hope you all understood. Now, okay, this will be enough if it is asked for some 3-mark question. If it is asked for some 5-mark question, then we have to prove it, isn't it? So what I am going to do is, in order to study the variation of the diode, I am going to solve the same with reference to our potential divider circuit. So I have drawn a potential divider biasing compensation circuit. So we have VThevenin here and an RThevenin here. Okay, what is the value of VThevenin? We know that VThevenin is equal to VCC into R2 divided by R1 plus R2. And what is the value of this RThevenin? RThevenin is equal to the parallel combination of R1 and R2, that is R1 R2 plus R1 plus R2. So this is the equation for VThevenin and RThevenin. So we have VThevenin, RThevenin, VCC. The current flowing through the VCC, here it is IC, here it is IB, and here it is IE. Okay, now see here, this is base, emitter, collector, isn't it? We have base, emitter and collector terminal here. So how can I say this is my VBE? Can you see it? This is my VBE, that is, here it is positive and here it is negative. So how will we connect this diode? Negative, positive phase opposition, and the diode should be made of the same material as that of the transistor is made. Okay, now we have to find out, is there any variation? Okay, so how can I find out? So the same operating point I am going to find out. So we know that we are finding operating point in 3 steps, isn't it? We find operating point in 3 steps. What is the first step? First step, we are applying Kurchwa's voltage law in the input loop. Okay, so how will we apply Kurchwa's voltage law in the input loop? What is the input loop? You know, this is my input loop, isn't it? So this is my input loop. So what I am going to do is, I am going to apply Kurchwa's voltage law in my input loop. So what I am going to do is, okay, I forgot, this is my input loop, isn't it? This is my input loop. I'm sorry, I made a mistake. As usual, I used to try like this. No, this is my input loop. So my input loop, I am applying Kurchwa's voltage law in my input loop. Then I will get VTH minus IB into RTH minus VBE minus IERE. Can you see it? Okay, minus IERE plus minus plus. So it is leaving from the positive terminal, plus VD is equal to 0. I hope you understood. This is my input loop, that is VTH minus IBRTH minus VBE minus IERE plus VD is equal to 0. So what we will give, I will replace this IE. IE is equal to IB plus IC. So I can write my equation as VTH minus VBE minus IB into RTH, and this RE plus RE minus IC into RE is equal to 0. So now what we will find out from the Kurchwa's voltage law? We have to find out IB. IB is equal to VTH minus VBE minus IC RE divided by RTH plus RE. Okay, so you got this equation, isn't it? Now what we will do is, we will substitute this IB in our IC value. What is IC? IC is equal to beta IB plus beta plus 1 into IC BO, isn't it? IC is equal to beta IB plus beta plus 1 into IC BO. Then what I have to do? I have to substitute here. Okay. So if I am substituting here, so in order to study this variation against VBE, we just have to study about the IB only. But still I am writing it. Okay. Beta into VTH minus VBE minus ICRE. I'm sorry, we have forgotten the term VD. So we have plus VD is equal to 0. Okay. So I'm sorry, I forgot the term VD. So here also if we are writing VTH minus VBE, here also one VD term is there. So if you are substituting, then we have another term, that is plus VD plus beta VD beta IB plus beta plus 1 into ICBO. Here we have RTH plus RE. Okay. So if I am substituting or rearranging it, then I get VTH minus VBE plus VD. I can write it like this. Okay, because I had a VD term here, so if I am writing it, then I can include plus VD here. Then what I can do, there is a plus VD here, so what I can do is I can rewrite it as minus VBE. Here it is plus VD, isn't it? So I can write it as minus VD minus ICRE divided by RTH plus RE plus beta plus 1 into ICBO. I hope you understood it. So what is the equation now? So from this equation we know that when there is a change in VBE, this VD also changes because they are made of the same material. This transistor and diode is made of the same material. So if there is a rise in for plus 2.5 millivolt per degree Celsius, then the same rise in plus 2.5 millivolt is there, and since they are in phase opposition, plus 2.5 minus 2.5, the changes are neglected here or cancelled here. So like this, if we are connecting a diode in phase opposition, then we can compensate for the variation in VBE. So we have discussed on the biasing compensation against VBE. Okay, so this biasing compensation we are giving usually for the silicon transistors. Okay, silicon transistors, we are employing this for silicon transistors because in the silicon transistor or the silicon transistors is very sensitive to the temperature variation. Silicon transistor is very sensitive to the variation of VBE due to the temperature. Okay, in silicon transistors. Okay, so what we have done, I am rewriting again because I made a small mistake. So you don't have to make any mistake. That is, we are applying input loop, Kurchua's voltage law to the input loop, that is VTH minus IB into RTH minus VBE minus IERE minus, sorry, it is not minus, minus plus, so it is leaving through the positive terminal. Last session I have told you, last semester I have taught the same using in our basic electrical classes. So VTH, that is plus VTH minus IB into RTH, and it is leaving, so minus VBE and minus IERE plus VD is equal to 0. Okay, then we are substituting IE as IB plus IC. Then I can write VTH minus VBE plus VD minus IB into RTH plus RE minus IC RE is equal to 0, or I can write IB is equal to VTH minus VBE plus VD minus IC RE divided by RTH plus RE. Okay, and in order to find out the output current, IC is equal to beta into VTH minus, here I can take minus outside, that is minus VBE minus VD minus outside, minus ICRE by RTH plus RE plus beta plus 1 into ICBO. This is the equation. From here we know that when the VBE varies with degree Celsius per degree Celsius, then this VD also changes with the VBE. So if there is a 2.5 millivolt variation for a temperature rise, then here also 2.5